Hello everyone, welcome to this introduction to integration and anti-differentiation. Recall that up until now you have been given a function and asked to find its derivative. Now you are going to be given the derivative and asked to find the original function. This process is called anti-differentiation. Differentiation and anti-differentiation are inverse operations of each other, just as addition and subtraction are, multiplication and division are, and squaring a quantity and taking the square root of that quantity are inverse operations. Anti-differentiation is the process of finding the set of all antiderivatives of a given function. You are going to notice throughout the problems that you are always asked to find an antiderivative, not the antiderivative. There's a reason for that. In general, and we read this that you see on the left side of the equal sign as the antiderivative of f of x dx is equal to capital F of x plus c. Let's dissect the different parts of this. F of x is what we refer to as the integrand. Think of another term you have learned in mathematics, the radicand, which is the number underneath a radical symbol, a square root symbol, for instance. The number you are taking the root of is what we always called the radicand. Here, the function of which you are taking the antiderivative is called the integrand. The dx that you see there is what we refer to as the differential. It indicates the variable of integration. Capital F of x is the antiderivative. Finally, the plus c is our constant of integration. Remember how we said before that differentiation and anti-differentiation are inverse operations of each other. Therefore, it will be true that the derivative of the antiderivative of f of x dx simply is f of x. In accordance with the fact we know differentiation and anti-differentiation are inverse operations of each other, the derivative and the antiderivative essentially undo each other. The power rule for integration, therefore, states that if n is an element of the rational numbers, remember q is the mathematical symbol for the rational numbers, because q is for quotient, and a rational number is a number that can be expressed as a fraction, as a quotient. So if n is an element of the rational numbers, but n cannot equal -1, hopefully it makes sense as to why, we'll talk a little bit more about that in a little bit, then the antiderivative of x to the n dx is equal to x raised to the n plus 1 power divided by n plus 1. So you're adding 1 onto the exponent and then dividing by that new exponent, plus c. This is the rule that hopefully you figured out for yourself through our introductory activity. A couple things to note though. Consider the antiderivative of x to the -1 dx, which can be rewritten as the antiderivative of 1 over x dx. You cannot use the power rule for integration on this, because if you add 1 to the exponent and then divide by that new exponent, you end up dividing by 0, which we all know you cannot do. That means we need to come up with another way to get the rule for the antiderivative of this function. Thinking of the fact that derivatives and antiderivatives are inverses of each other, can you think of a function that you take the derivative of and get 1 over x as the answer? Hopefully you thought and remembered that if you take the derivative of natural log of x, you get 1 over x. Therefore, the antiderivative of 1 over x dx is the natural log. Now we do say it's the absolute value of x. There is a reason for that, which we will investigate in one of the later lessons, plus c. This right here becomes the first rule you need to memorize. one of the special antiderivative rules. The antiderivative of 1 over x dx is natural log of absolute value of x plus c. Let's consider exponential functions with the number e. Remember that the derivative of e to the x is e to the x. We talked about that it's the only function which is its own derivative. Now let's think about antiderivatives though. Can you think about what the antiderivative then of e to the x dx would be? In other words, of what function is e to the x dx the derivative? Or what do you take the derivative of and get e to the x as the answer? Hopefully you figured this one out. The antiderivative of e to the x dx is simply e to the x plus c. This is the second rule you need to memorize. I like to think it's a pretty easy one. E to the x is a very, very special function. Again, it's the only function which is its own derivative. It's also its own antiderivative. What about exponential functions in general though? What if we want to discover a rule for the antiderivative of a to the x dx? A would be a number. So think, what function do you take the derivative of and get a to the x dx as the answer? This one's a little trickier. You have to think a little bit about this and be a little bit more creative. We find that the antiderivative of a to the x dx is 1 over natural log of a times a to the x plus c. This is the third rule you need to memorize. Let's look at a little proof as to why this is. Remember that derivatives and antiderivatives are inverses. So if we were to take the derivative of this answer, of the antiderivative, we should get that integrand back again. That's one of the great things about antiderivatives that we didn't have with derivatives, a way to actually check our answers. So let's take the derivative of this and see what we get. 1 over natural log of a, that's really a number. It's a numerical quantity, so that's our coefficient that would just remain as we take our derivative. Now we need the derivative of a to the x. So think back to your derivative rules. The rule for a derivative of a to the x is a to the x times the natural log of a. But look what happens. The natural log of a's cancel out, leaving you with a to the x, which is our integrand. As you work through antiderivative problems on your own, oftentimes you will have to rewrite that which is to be antidifferentiated by using some algebraic manipulation. For example, if we wanted to do the antiderivative of 5 over square root of x dx, the 5, just like a constant when you're doing derivatives, can simply come out in the front. We're going to bring that square root of x up from the denominator and rewrite it as x to the negative 1/2. Then we can apply the power rule for integration. Similarly, if we wanted the antiderivative of cube root of x times the quantity x minus 6 dx, we're going to think of the cube root of x as x to the 1/3 and distribute it over that quantity. And we arrive at x to the 4/3 minus 6x to the 1/3. Once again, you then apply the power rule for integration. Finally, one last example. If we wanted the antiderivative of x to the 7th plus 4 over x squared dx, we're going to apply the laws of exponents and rewrite this as x to the 5th plus 4x to the negative 2nd. Very similar to how you would have worked with it if you wanted to take a derivative.